Hi class, this is Mr. Morris, continuing our Pre-AP Chemistry Solutions crash course. We want to talk about the rate of dissolving, sometimes called the dissolution rate. This is only talking about how quickly something will dissolve. It does not tell us how much will dissolve, just how quickly something will dissolve. So dissolving occurs when the solute and solvent particles, or molecules, collide with each other. So if you want to increase the rate of dissolving, if you want to make it happen faster, what you have to do is increase the number of collisions. There's three ways we can do that. We can agitate the mixture by stirring or shaking. We can increase the surface area by crushing, or we can increase the temperature. We're going to talk about each of those. All right, agitating the mixture. Why is it that that would make something dissolve faster? Well, the reason is because if you agitate the mixture, that forces the molecules to move around more. As a result, more collisions take place between the solute and the solvent particles. And if you get more collisions, it dissolves faster. All right, if we increase the surface area of the solute by crushing it or breaking it or grinding it into smaller pieces, you can think of it as if you had a clump of something and you just crushed it down, it's going to spread out and have more surface. If you've got a greater surface area for things to interact with, you're clearly going to have more collisions between solute and solvent particles. And that is why crushing things into smaller particle sizes is also increasing the surface area, and it increases how quickly something will dissolve, or the rate of dissolving. So which of these types of sugars would dissolve faster? Granulated sugar or sugar cubes? Hope you know the answer to that would be granulated sugar. It would be granulated sugar. So if you're following along with your notes, you could bold that or underline it. That's the one that would be faster, that would dissolve faster because there's a greater surface area, there's smaller particle size. All right, if we increase the temperature of a solvent, it also can make the dissolving happen faster. Why is that? Well, remember that if you increase the temperature, you increase the average kinetic energy of particles. We talked about that with gases. So the particles move faster, which leads to more collisions between the solute and solvent particles. And again, if you have more collisions between the solute and the solvent particles, it's going to dissolve faster. All right, let's look at solubility. That's different. Let me back up just a little bit. That's different than rate of dissolving. Rate of dissolving is how fast something dissolves. Solubility is how much will dissolve. So if I want to dissolve more of something, I've got to change something that is different, okay? Now, temperature is the one thing, and I want you to know this, temperature is the one thing that increases the rate of dissolving, and it also affects the solubility. But agitating, so stirring, or increasing the surface area by crushing, the first two, they only change how quickly things dissolve. They do not affect how much will dissolve. All right, solubility is the amount of a given solute that will dissolve in a certain amount of the given solvent. So it is how much will dissolve, not just how quickly, but how much will dissolve. All right, the first factor we need to look at that impacts or affects the solubility is polarity. So the rule again is like dissolves like. If you've got a polar solute, it's going to dissolve in a polar solvent. It will not dissolve in a nonpolar solvent. Okay, so we've talked about that a little bit. We'll talk a little more. Pressure. Now this one only affects gases. Make sure you know this. Pressure only really affects gases. But this is called Henry's law. Gas solutes have greater solubility, so more will dissolve at a higher pressure. Henry's law has no effect on solid or liquid solutes, though. That's kind of the exception. It doesn't have any effect on solid or liquids, only gas solutes. The temperature. Again, temperature is the one thing that has an effect on both the rate of dissolving and the solubility. As a general rule, when you're dissolving something, As temperature increases, the solubility tends to increase. That's true for solids and liquids, for solid and liquid solutes. But if we're trying to dissolve a gas in a liquid, it's different, okay? Gas solutes are the opposite. As you increase temperature, they become less soluble. As you decrease temperature, they become more soluble. So gas solutes are more soluble at lower temperatures, less soluble at higher temperatures. Okay, to go back over each of these in a little more detail, keep in mind you can tell if something is polar by whether or not it will dissolve in water. So if I say something dissolves in water, since water is a polar solvent, we can assume that if it dissolves in water, there's a good chance it is a polar solute. So sugar, tea, coffee, Kool-Aid, etc., those are all considered polar. It could also be an ionic compound depending on how it dissolves, or an acid or a base. Substances that do not dissolve in water, such as oil and sand, are nonpolar. So if they don't dissolve in water, they're probably nonpolar. Okay, let's look at how pressure affects, in a little more detail, how pressure affects solubility. Henry's law says that the solubility of a gas solute is directly proportional to the pressure of that gas solute. In other words, the higher the gas pressure, the greater the solubility of the gas. And the lower the gas pressure, the lower solubility of the gas. So what this really means is if you want to dissolve gas in a mixture, you have to do that at high pressures. If you have a low pressure, the gas tends to bubble out of the solution and to go out into that low pressure area outside of the solution. So it comes out and does not stay dissolved. This is going to become very important later in the year when we talk about something called equilibrium. I want you to know that pressure only affects gases in solution. It does not affect solids or liquids in the solution. So our example here, soda contains carbon dioxide gas that was dissolved at really high pressures. That's why when you uncap a bottle, you can hear it fizz and you can hear the hissing sound. You start to see it fizz and bubble. That's because the gas molecules that are dissolved in the soda are less soluble because we decrease the pressure. When you open a bottle, you decrease the pressure. That's what we say here. The pressure is decreased. So the solubility of the gas decreases. And what happens? It comes out of the solution. And gases, when they come out of solution, go up. They come up into the atmosphere. And then temperature. All right. With most solid solutes, as the temperature increases, so look at the scale, the X scale is temperature. As temperature increases, then the solubility, the amount that would dissolve, also increases. You can see these upward slanting lines. Okay? But we have a downward slanting line. There's one exception. Now, gas solutes, they are the opposite. As temperature increases, the solubility is decreasing. That's why we have a downward slope. It's an inverse relationship between temperature and solubility. So know that solid solutes become more soluble with higher temperatures. Gas solutes become less soluble with higher temperatures. To help you remember that with gases, think about where you want to keep your soda. You want to keep it capped so that the gas does not come out of the solution, but you also keep it in the refrigerator in order for it to keep longer. So low temperatures, high pressures, that's how you're going to have the greatest amount of solubility if it is a gas. All right, degrees of saturation is probably the last thing I'm going to do on this video, and then we'll pause and come back to another one. We have 3 different degrees of saturation. We've got unsaturated solutions, saturated solutions, and supersaturated solutions. Those are the 3 different types of, or 3 different degrees of saturation. An unsaturated solution is a solution in which less than the maximum amount of solute that can be dissolved under the given conditions is dissolved in the solution. So what that means is I've got less solute dissolved in the solution than what is possible. It's possible to dissolve more than what I already have. In other words, more solute could be dissolved if it were added under the same conditions. And we could test that. We could add a little more solute, stir it up, and if it dissolves, we know it was unsaturated. All right, saturated solution is a solution in which the maximum amount of solute, exactly the maximum amount of solute that can be dissolved under the given conditions, is dissolved in the solution. And by the given conditions, we're talking about things like temperature and pressure and all that kind of stuff. In other words, more solute could not be dissolved if it were added under the same conditions. So I could test that. I could put a little bit more solute in and stir it up. And if it will not dissolve, then I know that solution was saturated. Note that if we have undissolved solute, undissolved means it's still a solid just sitting in the bottom of the container. If you can still see undissolved solute in the container after thoroughly mixing, we say the solution is saturated. There's some extra solute at the bottom, but the solution is saturated. Supersaturated is weird, okay? So supersaturated is the one that is unstable. It's a solution in which more than the maximum amount of solute that can normally be dissolved under the given conditions is dissolved in the solution. So let me say that again. More than the amount that can normally be dissolved is dissolved. And I don't mean that it's in the container, I mean it's dissolved. You can't see it. It's completely dissolved. Since more solute is already dissolved than normally possible, and this is an unstable state, remember, if more solute was added to a supersaturated solution, the dissolved solute, the stuff that's already in the solution, would precipitate out of the solution or crystallize, so it turns solid. I'll try to find a video and link it so that you guys can watch a video of this experiment. It's pretty interesting, okay? Note that to make a supersaturated solution, the only way you can do that, remember, if we increase the temperature, solids are more soluble. So you can heat it up to the point where you can dissolve more solute in, and you dissolve more solute than what is possible at room temperature and slowly cool the solution down to room temperature. That's how you get a supersaturated solution. And then when you drop one little bitty crystal in, it makes the solution, all of the solute just fall out of the solution. And you end up with either a precipitate or crystallization of the entire mixture. All right, seeding is how we test the level of saturation in a solution. Seeding is what I just talked about. It's adding a small amount of solute, sometimes we call it a seed crystal, to a solution and observing what happens. So we're going to look at an example on the next page, and hopefully you can identify what type of solution we're talking about. So in this example, a seed crystal is added to each beaker, and we want to determine the degree of saturation of each. So the first one, if I dropped a seed crystal into it and it just dissolved, what kind of solution was this before I put the seed crystal in? You got to think about that. All right, and then this one, if I drop a seed crystal in and I stir it up, it doesn't dissolve. It just settles to the bottom. We got to think about what kind of solution that would be. And then finally, if I drop one in, and as soon as it hits the solution, everything crystallizes. What type of solution is that? I hope you've got it. If it dissolves, it is unsaturated. If it settles to the bottom without dissolving, that's a saturated solution. But if it crystallizes, then what that means is before I put the seed crystal in, it was a supersaturated solution. Now please note that if you drop a crystal in and a bunch of precipitate falls out, it was a supersaturated solution, but now it is a saturated solution with solute sitting at the bottom. Kind of a weird concept, but once the excess solute falls out of the solution, it's no longer supersaturated. It's now a saturated solution with extra solute sitting at the bottom. I'm going to pause the video here, and I'll pick up with the next topic, reading a solubility.